Hi, welcome back to Azwanase channel. This is my second session for strength of materials. Okay, in this session, I will share how to draw shear force and bending moment diagram for distributed load. For the first session, I share how to draw the diagram for concentrated load. There's two different things between concentrated load and distributed load. It's okay. I will share it the difference between the concentrated and distributed load later. All right. Okay. In this sharing session, I'm very sorry because I'm not prepared any presentation slide, so I just write down on a paper. All right. Okay. This is my finger. Okay. This is my finger. It's pretty, huh? We got a ink stain here. It's okay. Maybe our session will become more attractive with my colorful finger. All right. This is my this is our question here. This is our question. So we have a distributed load. So we have a distributed load with a 10 kilonewton over m. Okay. You have to remember and you have to understand there's three types of load. One is a concentrated load. Concentrated load, usually there is only one single arrow, okay, or horizontal here. Vertical, horizontal. This one is a concentrated load. If there is a beam here, the vertical load act on the beam. This one is a concentrated load. But if you have so many arrows of force here, this one is a distributed load. All right. The other one is a concentrated moment. All right. That one is three types of load. Okay, back to our question here. You have to understand our question. So we have a beam, we have a distributed load at 10 kilonewton over m, and we have a two support, pin support at point A and a roller support at a point B. And the length of the A to B is a 3.6 meter. Okay, before we start anything, you have to remember our three main steps, just like what I have shared to you in the first session. The first one is FBD. You have to draw the FBD. The second one is you have to summation of F. I declare upward is a positive. All right, equal to 0. And the third one is a summation of M equal to 0 with the clockwise is a positive. All right. Okay. We go to the first step. You have to do our free body diagram. Okay. This is our beam and this is our arrow for distributed load. Okay. The corresponding force for the pin support, there is a vertical and horizontal. Our horizontal here is equal to 0 because along the beam here there is no other horizontal force, so that means is equal to 0. For the roller support, we have a single force. Okay, all right. Then we have a length here 3.6 meter. Okay. Okay, we have to find um, representative force. Usually, the representative force for distributed load for rectangular shape here is the center. At the center here, this one is a representative force for distributed load. All right, the length from A to the representative load, representative force is half of the length, half of the full length, so it will become 1.8 meter and the rest is 1.8 meter. All right, so this is our free body diagram. done part 1. Okay, we go to the second step, summation of f equal to 0. So summation of f equals 0, and I declare upward is positive. Alright, so how many forces do we have here? Okay, you have to count the forces first. 1, 2, and 3. So that means there is 3 values of force that you have to sum out equal to 0. The first one is at a VA here. We call this at a VA. VA is a upward direction, so it's a positive. The second one here, representative load is okay. We have to uh, count. Okay, how what's the value for the representative load? Okay, how you just multiply 10 Newton over m multiply with the distance 3.6 meter, cut off for the m, and you can get 36 kilonewton. All right, 36 kilonewton this point. Okay, all right, so that's mean we have a VA for the relative here, downward negative is against what we have declared the direction. All right, negative for the force here. So 36 kilonewton and plus VB equal to 0. All right, so you solve the equation, then you get VA plus VB equal to 36 kilonewton, and I named this equation as 1. Okay, next we go to the third step here. The third step is a summation of moment. All right, summation of moment at point B. All right, equal to 0, and I declare clockwise is a positive. All right, we go back to our free body diagram. So how many moment do we have here? We don't have a moment sign, right? But we have three forces. These three forces will develop a moment. All right. This one is 1, 2, 3, three forces. So that means there will be a 3 moment. All right. For the VA here, you have to multiply with distance to develop the moment. All right. What's the distance? The distance is 3.6. Okay. This one is a positive or negative? All right. Moment positive or negative? Okay. Just like what I have told you in this first session. Okay. Okay. Remember my beam. All right. At point B here, I hold at the point B here, so there is a upward force. That means the beam will bend will rotate clockwise. Okay, clockwise. So clockwise is follow what we have declared earlier, positive, so it becomes positive. So the next one is the force. The representative force is a 36 kilonewton. 36 multiplied with 1.8, the distance between the representative force to the point B. All right, 1.8. Okay, it's not clear. All right, 1.8. So what's the sign, positive or negative? Take back our beam. There is a downward force here. That's mean the beam will rotate anti-clockwise against what we have declared. So it becomes negative. Why my arrow here is not complete? Okay, you can see here my arrow there, right? Then the third one is the beam, the force at the VB, but the distance here, you have to remember this. This one is the F, this one is the D. This one is the F, this one is the D. Alright. VB here, we have a force for VB and multiply with distance. What's the distance here? The distance is 0. Okay, let's say it's a positive. Alright. Negative equal to 0. So that means you have to solve this equation. Then at the end here, you will get VA equal to 18 kilonewton. We have to solve it. Alright. Okay. Okay, from the VA equal to 18, from this value, get this value into our equation 1. Okay, into our equation 1, VA plus VB equal to 36. So VA is 18 plus VB 36. So VB is 18 kilonewton. Alright. Okay, then we have to do the imaginary card. You still remember the imaginary card? If you forgot about the imaginary card, you have to refer back to my first session. Alright. Okay. I will do the free body diagram. Don't worry. If you want to do the imaginary card, you have to remember these three important things. Yeah. Free body diagram, summation of F, and summation of M. We go for free body diagram. This is our beam. Let's say I do the imaginary at this point. This one is our beam, and this one is my force here. The VA equal to 18, and there is this one, the value is X. Okay, we still have a distributed load. With 10 kilonewton over M, and we have a representative load for distributed load here. Okay, the distance is half of the length. This one, when you cut at this point, so they must have a internal shear force and internal moment. I name it as V cut, and this one is moment cut. Alright, this one is a X over 2. This is our FBD. After done for the FBD, alright, for the first section, I just want to share something. If we have a distributed load here, we just do only one cut, only one imaginary cut. Okay, only one imaginary cut, because if you, this is not concentrated load. Okay, this is just a imaginary. This one is only a representative force for distributed load. So we only do one cut only. Alright. Okay. Now we go to summation of F. We go to summation of F equal to 0, and I declare output is positive. So how many force do we have here? 1, 2, 3. The first one is 18. It's upward direction, yeah. 18 is an outward direction, so it's positive. And we have the second force here. Okay, what's the value for this force? The value for this force is we have a 10 kilonewton here, 10 kilonewton over M multiplied with the X value. The X value is in meter, so we can cancel out the unit meter, and at the end we can get 10x Newton. Alright, this is the value for our representative force. Okay, that means it's a downward direction against what we have declared, so it becomes negative 10x. All right, plus, oh sorry, minus again. So we cut here is a downward direction, so it's against what we have declared, and we get negative. Negative v cut equal to 0. All right, so you simplify this equation. V cut equal to negative 10x plus 18. All right, so we get a linear equation. That means in our shear force diagram later we have a linear graph. Okay, let's say if the x value is a 0, okay, the v cut the shear force will become 18. Okay, 18. Okay, that means at here, if the x value is 0, so the shear force is 18. All right, and if we have x equal to 3.6 at this point, so the shear force value will become 0. Okay, what happen if x equal to 1.8? If if 1.8 here, the x value will become 1.8 become 0 again. All right, next we go to our summation of moment. Yeah, summation of moment. For the summation of moment, I declare it at a point cut equal to 0, and I also declare clockwise is a positive. So how many moment do we have here? Okay, we have a one moment and three forces, which all these force will develop a moment. So the first one is 18. The first one is 18. Multiply with x. Multiply with x. This one is a F and this one is a D. Alright. This one is a positive or negative. Okay. Remember our beam. Okay. I hold at the point cut point here. So there is a force here. So that means it will rotate clockwise. Okay. So that means it's positive. Is follow what I declared earlier. So what about at representative point here? Representative force. We have a 10x. Okay, multiply this one is a f, and distance is x over 2 from the representative force to our cut point. So we have x over 2. So the sign should be positive. Okay, there is a force downward there, so it's going to be anti-clockwise. Oh, if anti-clockwise is against what we have declared, so it becomes negative. All right, so at this point here for the v cut, okay, for the v cut, we don't know the value, but it will multiply with 0, right? Multiply with 0, so it becomes positive. It can become 0, so you can put positive minus m cut equal to 0. Okay, the m cut here is a negative because it's against the direction what we have declared earlier. All right, then you solve the equation. You just solve the equation. At the end of the equation, what you will get? Okay, you will get negative 5x power negative x power to 2 plus 18x equal to 0. Alright, this one is a quadratic equation. You can imagine your bending moment diagram later will have a quadratic graph. Alright, okay. Let's say if the x value, is, wait, yeah, okay, if the x value is 0, what happened to the moment? If the x value is 0, if x value is a 0, so the m moment will become a 0. If the x value is 3.6, the m value will become 0 again. Right. Okay, you have to calculate that one. Okay. And if we have a x value 1.8, your moment will become 16.2. All of these things is a kilonewton meter, kilonewton meter, kilonewton meter. All right, done for summation of m. For the final part, we are going to draw what? We are going to draw a shear force diagram. Okay, shear force diagram. This one is our x, and this one is our v. Okay, the unit is kilonewton. This one is x. The unit is m. All right. Okay. This zero value. You can see there. If the zero value, the x is 0, the v will become 18. We just one dot here. Okay. Back to our equation. V cut equal to negative 10x plus 18. You have to remember back your general equation for linear equation. Y equal to mx plus c. Alright. If the m value is negative, the graph will be, the slope is downward. Alright. So, well, you can see here, this one, if the x value is 1.8, and this one, if the x value is 3.6. For the 3.6 here, the value of v is negative 18. Alright, so the point here, we have at this point. So we got another point here. At 1.8, x equal to 1.8, you will got a shear force value at 0. So our linear equation for our linear equation, oh sorry, 1.8. Okay, you can see there. Okay, here is your shear force diagram. For moment force diagram, okay, we have a moment here, we have moment, we have x axis here. Okay, moment, we have kilonewton meter. Alright, x is a meter. Okay, this one, the zero value. Alright, this one is a 1.8, and this one is a 3.6. Okay, so we have a quadratic graph here, right? For the moment, quadratic. Okay, you have to remember the quadratic equation. If the value is a negative here, so you will get a graph like a sad trine. If positive, you will get smile trine. Okay, now we have a sad trend. If you have a sad trend with the at the point x, we have a 0. The moment is 0. If you have a 3.6, the moment is also 0. And at the point 1.8, we have a 16.2. We have a 16.2. Okay, let's say this one is a 16. 16.2. We have a 16.2. All right. Okay, then our graph is what negative is a set trend, right? So that's mean we have this kind of graph and quadratic. Okay, this one. Okay, finish. We have a shear force diagram, and also we have a moment for a moment bending diagram with a maximum point at 16.2 kilonewton meter, and here we have a maximum shear force is 18. Yeah, 18. Maximum shear force, sorry, maximum is 18 kilonewton. You see the force here, and the maximum moment is 16.2 kilonewton a meter. All right, complete. Thank you.